I want to welcome you to another multivariate statistics class. Of course, the focus today is going to be on the reminder of the material for last week. Of course, we're not able to finish the multivariate normal density, so that will be the focus today. Um, I've updated this material and of course it's already been uploaded. I needed to check Canvas. So I actually call this multivariate normal density part two. Um, you know, I remember last week I started you started with multivariate all the way to bivariate. Then we are on multivariate, but we're not able to finish the material. So I'm actually going to walk us through some area of application, specifically examples under multivariate. Then I'm also going to be extending multivariate normality into sampling distribution, just like the way we have it in the univariate case. Okay, so in the focus today, you're also going to learn using multivariate normal density. How can we estimate parameters, okay, using the method of maximum likelihood as well. Okay, so I left you with this example last week. Each delicious candy company store makes three size candy bars, regular X1, front size X2, and big size X3. Assuming the weighting on sales of the candy bar S1, S2, S3 follow a multivariate normal distribution with parameters. Now, when you take a look at what I have, the parameters are 537, and the covariance matrix also given. Suppose we select a store at random. What is the probability? A, the weight of a regular candy bar is greater than 8 pounds. If you take a look at A, okay, if you take a look at question A, we got three different kind of variables, but question A is only focusing on one variable. And the variable is focusing on is the regular candy. The regular candy is X1. Don't forget, we also have font size. We also have a big size. So if you take a look at A, we're only going to narrow down to, to that particular variable only. So if I want to, have a probabilistic computation involving that particular variable, I only need the mean and variance, okay, or the mean and standard deviation to be able to move forward. And that is the reason why when I started, you can see here, okay, give me 1 second. I'm gonna see if you can. Okay, so when you take a look at this guy, okay, I think that is not writing. I'm gonna choose a different one. Don't know why that is not showing. Uh, let me see if I can choose a different one. Okay, so, okay, now you can see where the pointer is right now. So X1 follow, so because I'm only focusing on regular candy, so it's X1. So I'm only, it's more or less working with univariate. Okay, now what I'm actually going to do, since I've identified that from the data given, this is the mean, okay, and this is the variance for that particular data set. I told you in the variance covariance matrix, of course, the diagonal are the variances. Okay, so I just bring that out to be this one. Now, I'm just going to go back to the lower level statistics. You know, how if I have something like this and I want to find probability, okay, of a random variable greater, okay, of course, I'm actually, from a standardized, the Z, okay, you remember it's X minus mu over standard deviation. So that is exactly what we're using here. So here, 8, okay, is the guy here, okay, minus the mean is 5. The standard deviation is going to be 2 because the variance is 4. The square root of 4 is going to be 2. Now, the moment, so what I want to figure out is probability of x1 greater than 8, and what I end up in getting will be probability of a z greater than 1.5. And z is a standard normal, it's a z-score. And with a z-score, I can check normal table, or I can use, a coding out. Okay. So if you take a look at what I have, whenever you have something like that, it's going to be 1. When you get to that junction, it's going to be 1 minus p norm. 1 minus p norm. Okay. 1 minus p norm into parentheses 1.5. If you put that in your in R, 1 minus p norm automatically is going to give you this result. Greater than when you're seeking the probability of a z-score, for greater than is going to be 1 minus p norm. For less than, it's just going to be p norm. And that's how that is settled. Is there any question on this page before I move to the next page? Go ahead. What, can you say that again? Oh, okay. So you want me to remind you what they means, right? Okay. So that very P, should I start with P? That P means it's a notation for probability. The fee. Oh, okay, okay. Give me 1 second. I want others to see it as well. I know you mean this guy, right? Okay. That very guy is telling you, go to table. It's like telling you, go to the normal table to check. Does that make sense? So if I want to go to the normal table, like, let me first tell you, one minus file of something is because I have a greater down. That's how I do 1 minus 5. Now, that phi of something now is just p norm in R. That's a very good question. Just p norm. Does that answer your question now? Okay. Okay, so we've that is the probability now. Okay. And if you want to make a sense of this, multiply that guy by 100. If you multiply by 100, because when you just have it in probability form, it doesn't make sense. Like if you want to interpret to us, so somebody that is not in this feed, don't forget, if I multiply this by 100, that would be like 6 points. Let me just say about 7%. So what I'm trying to say, about 7, if you go back to the question, okay, about 7% of the candy, the regular candy they are talking about, will have their weight greater than 8 ounce. That's what it means. Okay, about 7%. We have their weight. Okay, the weight greater than 8 ounce. That's what it means. Okay, now I'm actually going to go to question B. Question B said the weight of a regular candy, is he talking about regular candy, X1, okay, is greater than 8 ounce, given, now I needed to pay attention to given that the font size bar weigh 1 ounce and the big size bar weigh 10 ounce. That's a conditional. That requires the use of a conditional normal distribution. Now, if I want to interpret that, okay, the interpretation is actually here. You need to first interpret mathematically. Take a look at that. Oh, I actually want to find x1 I'm interested in X1. X1 is the weight of the regular candy, okay, greater than something. So I'm interested in X1, given that I already know S2 it to be something and S3 to be something. And you know what? This is a conditional, and this is also going to follow normal distribution. If I want to use the idea of a normal distribution, this random variable now, okay, it's a random, this guy now, it's a random variable, okay, since it follow normal distribution, if I want to find probability associated with that, then I need a mean. I need a conditional mean. I need a conditional standard deviation. Okay, and which is exactly what I want to find. Okay, right now I am seeking because if I don't get mean, if I don't get standard deviation, there is no way I will be able to use the idea of a z-score, because normality facilitates standardization. Okay, the further is normally distributed. If I want to have a probabilistic computation, then I'm actually going to go by way of a z-score. Now, and to go by way of a z-score, it means I'm going to standardize. I need my mean and the standard deviation to standardize. Now, based on this is now going to based on what you've learned before. How do we get the conditional mean? If I have three variables and one mean, okay, a variable is conditioning on the other variables, how do I figure out conditional mean? To figure out conditional mean, this is the formula. This is the formula ever that we're going to be using. Okay. Now, and this does not only apply to X1. A question can be framed again, maybe X3. It could be X3, giving X1 and S2 equal to something. You're still going to use that. You're only going to change your stuff. Okay. Now, if you take a look at the formula, if you take a look at the formula right now, you actually are going to see that a mu star is a conditional mean equal to the mean of X1. That is the mean of the variable that is conditioned on other two variable is the first one. Look at that here. That is the mean of the X1. Okay. Plus, okay, then you're now going to consider, okay, the covariance matrix for, take a look at that. Okay, this one now is actually it's talking about just this guy here. Look at that. Because those ones are the one that has to do with S2 and S3. Okay, those one that has to do with S2 and S3. Okay, and that's exactly what you're seeing here. Okay, and of course, I need the inverse of the covariance 2 by 2. Okay, which is definitely this guy here. Oh, give me 1 second. Which is this guy. That is a that is the position that guy is occupying. Okay, I wanted to take a look at it that way. Okay, so the splitting is like it's going this way. The splitting is like that. Okay, and this is the 2 by 2 aspect. If like I'm splitting the whole thing into, I'm splitting the whole thing into 2 by 2. Okay, so take a look at that. This is going to be 2 by, this is a 2 by, this is the 2. This is like, if I want to write it, this is 2, 2, sigma 2, 2. Okay, this is sigma 1, 1. You remember the other time? The sigma 1, 1. The sigma 1, 1, like S11 is a variance of X1. Does that make sense? And the other two that that we're focusing on, that's conditioning on, you consider covariance as well, not just 4 and 2. That was why you have all of that. Okay, now, if you plug in that, if you plug in, okay, you're actually going to get this result. Is there anyone who doesn't understand how to get 5.75? Is there anyone who doesn't understand that? Now, let me tell you this. Tomorrow night, I'm actually going to release practice question for midterm 1. And I'm seeing a lot of this inside it. Okay, let me tell you this. In your midterm 1, I'm going to allow calculator, and I'm also going to allow the use of laptop for software, maybe our software. Does that make sense? Okay, so when you use that for calculation, or what I just need is put your answer on the exam booklet, but more information are coming in the revision week. Okay, that's a conditional mean. Now I'm also going to go with a conditional. I also need, of course, I get a conditional mean. I also need conditional variance. Take a look at that. Okay, conditional variance. Okay, so if you take a look at that. You know, there's something I want you to pay attention to. Okay, if you take a look at this guy here, right? You're gonna see something now. And the first two in the variance formula, okay, let me go back. Can you see that guy? Also in the variance formula. Do you see the two? Okay. The third one is what is different, sigma 1, 2, because in the case of the mean formula, it was the difference between that. Please pay attention. And if this one is the first term here is unconditional mean for x1, then here is going to be unconditional variance for x1. Can you see that? Okay. Now, when you follow all of that, that is going to be your conditional variance. Is there anyone who doesn't understand something on this page? Is there anyone who doesn't understand how I got both the conditional mean and conditional variance? If you have your conditional mean and conditional variance wrongly computed, then that's going to be an issue moving forward. Okay, now after getting that, then we are ready to answer a probabilistic question. What was the question? Look at the mathematical interpretation. I needed to pay attention to this. Compare this to the first question. What do you see? You can see that guy was not, let me do this. You can see this guy was not conditioned on anything. Here, I want to find the probability of S1 greater than 8. Okay, I'm looking at the percentage of the regular candies greater than 8 ounce without conditioning on the other candies, on the weight of other candies. But right now, if you take a look at what I'm doing here, okay, I still want to find the probability that x1 is going to be greater than 8, but right now I'm conditioning, okay, on the information that I have about the weight of the other ones. And if I want to do that, I'm still going to, the only difference is just, you know, when you come here now, what I'm going to plug in here and what I'm going to plug in here. And that was what we derived. We derived the conditional mean, we derive the conditional variance, and every other thing that we do stay the same. And look at what we got here. And look at what we got here. Okay. You know, when it is conditioned on other variable, it's like the percentage increase. Can't you see that? The probability increase, like if you multiply that guy by 100, okay, it's going to be like 12%. But in the other one, it's about 7%. Okay, you can see. Okay, so the first one that we did actually ignore correlation among the variables, and the second one that we did not ignore the take into the consideration. Now I want to go into another question right now, which is going to be question C. The probability of 4x1 minus 3x2 plus 5x3 less than less than 63. You know, if I want to solve a problem like this, if I want to interpret, please pay attention. Okay. Please pay attention. If I want to interpret a question like that, here, give me 1 second. Okay. I'm actually going to rewrite this guy. Why can't I just write I want to find the probability, okay, of W, okay, less than 63. I can say that. Where my W is a linear combination, my W equal 4x1 minus 3x2 plus 5x3. Can you see that? Now, if I want to find the probability associated with W right now, what I'm going to do, I need the mean of W. I also need a standard deviation of W. Okay? I need the mean of W, the standard deviation of W. So if I need the mean of W and standard deviation of W, it is similar to what I gave you in the last assignment. Okay? Or what this is how it's going to be super easy doing that. Now, what I'm doing here is finding the mean expectation. That's what I'm doing there. And what is the expectation of 4x1 minus 3x2 plus 5x3? Or what I'm just going to do, expectation is going to be 4 multiplied by the mean of x1, 3 multiplied by the mean of x2, and 5 multiplied by the mean of that. Then I'm just going to have the mean to be 46. Is there anyone who doesn't understand how we got the mean to be 46 for this linear combination? Is there anyone? Like I said, do not hide your feeling. Our midterm is very close. Because even though you are having good result in the assignment now, okay, the major way for me to detect whether you really understand the message I've been passing across is when you have a supervised exam. And if you don't understand now, I will advise that you ask question. Okay, now when I after getting the mean, do you know that what I'm actually using here is more or less like what you did the other time that you call A prime mu? Do you remember that? A prime mu. What is A here? Your A is 4, -3, and 5. 4, -3, and 5. This is A prime mu. Okay, if I now want to get the variance, you remember the variance. Okay, that we're going to have that guy, you remember the formula, and that guy. You remember? You want to do that in matrix form. That is how you're going to get it. Take a look at what I'm going to show you now. Is that not what I'm using? Take a look at this guy. This guy now, the first, let me say this. This guy is your A, is a matrix A. Okay. And of course, you know that guy is this. And this guy is that. Anytime you're dealing with a linear combination, that is the approach to get the variance. And at the end of the day, I got the variance to be 289. If a random variable follow normal distribution and I'm seeking to get the probability associated with that particular random variable, if I know the mean and I know the variance, I will be able to move forward using the idea of a standardization. Does that make sense? I'm seeing a lot of exam questions here. A lot. A lot. Okay? Spare more time on this. Okay, now I'm ready now. I'm ready now to answer the question. Now, what do you think I put? The mean that I got computed, the variance that I computed, and of course, okay, look at that. And I got this probability of a z less than 1, then I'm going to, in R, it's going to be P norm of 1. And that's going to give me that. I'm done. Is there any question? Is there any question? And if you want to do everything in R, let me tell you this. The first, if you want to do anything in R, you need to first determine, you need to find your z-score. Okay, take it out. You need to find your z-score. Okay, if you take a look at this code right now, okay, like this one, you see that indicating the value 8 mean equal to that is equal to that. And even if you take a look at the question 2b, okay, what we are programming, if you take a look at the question 2b, the way we did it, okay, Here you are already assuming you know your mean. You know, we computed using the variance formula, the conditional mean formula, and you already know your standard deviation. You know, that's why you plug in that in. Automatically, arrow is not going to give you answer to the question. You need to first compute the mean and variance before you plug them in into the arrow code to generate. Okay, I provided an arrow code here. This is an arrow code for question A, B, C. I was so happy the other time when somebody was seeking clarification on a particular notation. So if I were you, if you get stuck, if you don't understand, or maybe you've done a particular notation before and you forget about it, and I will advise that you ask me question. My experience in teaching this course in Africa, Europe, and United States, I come to realize students struggle with statistics or mathematical related subject because of the fact that they have difficulty, getting familiarized with notations. If you understand what notation is, symbol represent, you're actually going to appreciate what you're learning. Now I want to move. The other time, I remember when you have a univariate normal distribution. Okay, when you have a univariate normal distribution, we actually use different approach. Like I remember we use method of maximum likelihood. Okay, method of maximum likelihood to estimate parameters of the distribution. Okay, and let me tell you this. We did that for univariate, and how we can also do that for multivariate. Okay, but if I want to do that for multivariate, I also need to specify the distribution. Okay, now we take a look at this. This is a multivariate normal density. Okay, if I want to use the method of maximal likelihood, I'm actually going to the joint. This guy is indicating joints are so many of them. They multiply in each other. Okay, now because I'm actually want to optimizing something that is multiplicative in nature, maybe tedious, and that is why we're going to introduce a log. You remember, I'm going to introduce a log. Optimizing a likelihood function is synonymous with optimizing log likelihood function, because when you take the log, okay, it's going to be in an additive form that will be very easy to differentiate. Okay, that is very easy to perform derivative on. Now we're going to perform derivative on the mu, differentiating with respect to mu set to 0. At the end of the day, what is it telling us? It's trying to tell us the sample mean vector is going to be equal to the population mean vector. You remember in the univariate case, the sample mean equal to population mean. In a multivariate case, the sample mean vector will be equal to population mean vector. Okay, and you can also seek the same to differentiate with respect to uh, covariance matrix. And at the end of the day, you're actually going to have this guy as a covariance matrix formula. Let me tell you this. What is the essence of what we're doing? The essence of what we're doing is we normally work with sample data. How am I going to know the formula that I'm actually going to use to find the mean vector, to find the variance vector, the covariance vector from the sample? This is how we derive it. This is like showing the first principle. Okay, the formula we use in statistical analysis or in multivariate analysis, we actually derive those formula using our mathematical knowledge. Okay, now I want to go into something else that we call sampling distributions. We all know, in a univariate case, okay, if because we're going to be using sample, if I want to figure out the average, if I want to figure out the mean, okay, if I give you, if I give you this assignment that you should go into this university, randomly select, maybe 30 students, okay, and you want to ask each of them how much they spend weekly on food. Okay, now because the 50 students in your cohort will be different from 50 students in another person's cohort, you're actually going to have different means. Does that make sense? If you are going to, you're going to have different average. And of course, you now have situation where we call that statistic, and statistic now vary. Okay. Now when statistic varies, now what you now want to do is you want to be able to find what is the distribution of the statistic, because you can find the distribution of what varies. Now, if you know the distribution of statistic, if it is normal, okay, then we can say, okay, we're going to find the mean of the mean, the mean of the averages. Okay, so that is more or less like you have 500 investigators working on the same thing. They have different results. Okay, if they have different results because they are using different samples. Okay, now what we normally want to do is when sample size is large, as given by central limit theorem, when sample size is large, the distribution of the statistic will converges to normality. Because we want normality. You know why we want normality? We want normality because the moment we attain normality, it will facilitate standardization. And when we're able to standardize, we will be able to have an easy probabilistic computation. Does that make sense? Now we now want to extend, the univariate to multivariate. The other time, and we're only focusing on one variable, where we believe that when we take a sample, repeated sample from a population, okay, and when the sample size is large, we believe that the mean of the means is going to be equal to the population mean. But this time around, we don't have just one variable. We have more than one variable. We want to talk about what I'm going to call, we're going to have a multiple joint statistic, as in joint statistic. Oh, okay. We want to talk about joint statistic, not just a single statistic. Initially, in the univariate case, we're having this X bar. This X bar varies, but right now, what is going to vary is X bar 1, X bar 2, X bar 3, until you will get to X bar P. Okay, and we also want to apply a central limit theorem that would say that when sample size is sufficiently large, the distribution of this, even initially, because initially maybe the variables that I'm interested in, those variables, they may not follow a multivariate normal distribution, even though each of them could follow normal, but jointly they may not follow normal. But when the sample size is large, okay, when the sample size is large, okay, they can actually they could be monthly normally distributed. Okay, they could be jointly normally distributed. That's exactly what we're trying to do here. Okay, now this is for the univariate case. Now, in the univariate case, we have already established that the central limit theorem play out. Okay, the sample statistic, follow normal distribution. Okay, with a sufficiently large sample. Okay, and the variance follow a chi-square distribution, because when mean varies, variance also varies. Okay, but in the case of if you want to extend this to multivariate case, okay, and I need you to pay attention now. Okay, if you take a look at this, okay, the first one, the sample mean vector, okay, the distribution, even if it is non-normal initially, okay, but with the last sample size, they're going to be normal. They're going to be multivariate normal. And let me also say this. Has anybody heard about the law of large numbers? Law of large numbers. Has anybody heard about that? Law of large numbers? Law of large numbers. Let me tell you, there's a difference between this and this. Central limit theorem. See, these two are very crucial in statistics. Okay. The law of large numbers states that when sample size is sufficiently large, sample mean converges to population mean. I'm going to say that again. The law of large numbers state that when we have sufficiently large sample, the sample mean converges to population mean. But the central limit theorem states that when you have a sufficiently large sample, the distribution of the statistic becomes normal. Does that make sense? Even if you're choosing from a population that is not normal, provided the sample size is large, the distribution of the statistic becomes normal. So what we're trying to tell you now, this is also being extended to multivariate case where more than one variable is involved. So the normality we're talking about in the central limit theorem in the multivariate case is multivariate normality. Does that make sense? And when they mean, when the statistic, the statistic in this case for the mean is going to be a mean vector, which means mean vector converges to population mean vector. That's what it means. I'm going to say that again. The sample mean vector converges to population mean vector. So which means the law of large number applies. Okay, but for the central limit theorem, okay, if the variables they were not jointly normally distributed before, when sample size is large, they will follow normal distribution. They will follow joint normal distribution. That is the central limit theorem in the multivariate case. Now, in the univariate case, the variance follow chi-square distribution, but in a multivariate case, it does not follow chi-square distribution, but it follow Wishart. This is Wishart distribution. Wishart is a generalization of a chi-square. Wishart distribution is a generalization of a chi-square. Now, what I'm telling you now, they will be very, very useful when we start new topic that we call, we try to start going to testing means in multivariate setting, hypothesis testing, confidence interval in multivariate setting. Okay, you're actually going to appreciate what I'm saying here. But do you know what I've included? If I'm working with variables, if I'm working with so many variables, how am I going to know in the first place that they follow normal distribution jointly? Let me tell you this: the fact that each variable follow normal distribution does not translate into them collectively or jointly follow normal distribution. It does not happen that way. So do we have a test? Do we have some tests, okay, that we can conduct if I'm working with variables, okay, before I will be able to see whether they follow normal or not. Yeah, we got several tests. Number one is this. I want you to pay attention to this. I'm actually simulating data here. Okay, I'm simulating data here. My X1 follow normal, my X2 follow normal, and my X3 follow normal. Okay, I'm simulating it now. Okay, but I'm simulating each of them from normal. Okay, and I want to demonstrate that it could follow when I conduct a test, it's either they all they are jointly normally distributed or not. So each of them following normal distribution does not guarantee, okay, multivariate normality. Okay, now I'm conducting a test. You see the test right now? So this particular test, you can see, which means if you have your data, okay, that contain, maybe you've already selected the variables you are interested in, okay, and if you conduct this test, now let me tell you, I need you to pay attention now. I need you to pay attention now. Okay, what do I have in the non-hypothesis of this test? What do I have in the alternative? The null hypothesis of this test is that the three variable follow normal distribution. Alternative that they don't follow normal distribution. Now, if I really want to take a decision here, okay, now I'm actually going to look at the p-value. Okay, let me tell you this. What this particular test is testing for is skewness and kurtosis, because skewness and kurtosis, they are departure. They measure the departure of the distribution of data from normality. That's why we're the testing skewness here. Now, when you take a look at the p-value associated with the skewness, the p-value is greater than 0.05 level of significance. Because of that, we're going to fail to reject H naught. Don't forget, I told you in this particular test, now H naught is that the variables follow normal distribution. Okay, all the variables, okay, they are, they're jointly normally distributed. Okay, that is the H naught. Why the alternative is going to go against that. Okay, now based on the one for skewness, the p-value is greater than 0.05. The one for kurtosis, the p-value is greater than 0.05. Then we're actually going to say the data follow normal distribution. Okay, now this is not the only test that we have in statistical literature. This is another one. This is called energy test. Energy test is very popular. Energy test. Now, energy test, okay, take a look at that. I'm actually going to look at the p-value associated. Okay, the p-value of the test is also greater than 0.05. Okay, so the p-value is greater than 0.05. Then we're going to fail to reject the non-hypothesis of the test. So we do not have evidence to say that the three variables in our data do not follow, which means they follow. Okay, since I'm not rejecting H naught. If you are working with a real life data set, okay, and because before you can actually use an approach that go with normality, you need to first investigate whether your variables follow normal distribution. Just like what I used to say, our models are not failing us. We are the one at times that we don't do the right thing. Okay. Now, the several tests. It's another one. Madia NVN test. It's another test. Okay. This test is also testing for skewness and kurtosis. Okay. Now, I'm using a real life data set here. If you load the library, if you load that package NVN and you have access to the iris data, of course, you'll be using iris data a lot in the in statistical world. Okay. And you're focusing on Setosa in the iris data. Okay, focusing on 4 variables, okay, 1 to 4. Take a look at that, okay, and you conduct the test. Okay, it's also basing it on skewness and kurtosis. You can see result. Yes, yes means if they follow normal distribution. The moment you see no, this is what I mean. Okay, take a look at this guy now. Okay, you can see yes. Okay, if you see that now, so then it follow normal distribution. That's what that guy is saying by by Madia test. So this apply Madia test on real life data set. Now I'm also going to apply an energy test on real life data set. Take a look at what I have right now. Okay. Now there's something I want you to see here. Please pay attention. Pay attention. When you go to inappropriate courts to seek for justice, you may not get justice. Okay. Now, and that is the reason if somebody commit an offense in a particular state, it should be tried with the law of the state he or she break, not with the law of another state. Now, there's something I needed to see here. Okay, I conducted a Madia test on Iris data, okay, and the results come positive that the distribution is normal. Then I decided to go and use energy test. But what you see in energy test, he said no. Now there's a conflict. It's just like you have judges giving conflicting judgments. The question is, well, which one are we gonna go with? And I need you to pay attention. Now, the issue, if you take a look at the data set, the data set here, okay, you're actually gonna see that we're talking about 50, okay, 50 sample size, okay. Energy tests normally work great with sample size less than 50. The moment the sample size is large, there's going to be an issue with energy tests. And that's why you can see here it said no, even though the distribution is normal, it said no. Okay, now the different kind of tests you conduct, they also have their limitation. Judge has a limitation. That is why we have an appeal court. Appeal court could have a limitation. That's why we have a Supreme Court. And in the Supreme Court, the number of judges in Supreme Court is even more than the one in the appeal. Okay, so just take a look at that. And at times, even a Supreme Court could take a case, could deliver, on a case, and after so many years, and then maybe they bring the case again, there's possibility the Supreme Court can overturn. So what I'm just trying to say is we also have the same in statistics where we are conducting a test and we need to for spend a lot of time understanding what is the limitation of the test. Every procedure, every technique in statistics, have assumptions. Okay, you have to make sure the assumptions are strictly followed. Okay, this is where I'm actually going to stop. Like I said, tomorrow night that I'm actually going to upload the midterm one practice questions, and of course, in the revision week. Of course, in revision week, in exam week, there's not going to be assignment. Okay, in the revision week, so I'm going to give you a lot of information about what you need to bring into the exam, and how you are actually going to solve a particular question. Okay, what the expectation is. So that all of that will be reserved for revision week. But like I said, you're actually going to have a normal traditional exam where I give you a booklet. You're going to be in class, and of course, what I need is the answer. Some requires workings. Okay, where you're going to show your work, but I'm actually going to allow you to use your calculator. I'm also going to allow you to use your laptop for software. Does that make sense? You're bringing it to the exam hall. Okay, I'm actually gonna have a question you can actually complete within 15 minutes. Okay, okay, is there any question? And of course, I'm also allowing a cheat sheet. Okay, of course, during the revision week, you'll be able to know, uh, what are the areas you're actually going to put in your cheat sheet. You can write in your cheat sheet. You can type if you like. I'm flexible. Does that make sense? Okay, this is where I'm actually. Um, okay, let me say this. Midterm one will only be the area that will be tested in midterm one is up to today. The topic that we're going to start on Wednesday is never going to feature in midterm one. So if you want to prepare for midterm one, everything that we have done up to today's Monday, does that make sense? Does that make sense, right? Okay, make sure you all stay safe. Have a lovely day. Bye for now, everyone.